Communication. Communication allows us to explain what we are experiencing or our feelings and needs to someone else, which not only helps us to meet our needs but also helps us to stay connected in our relationships, which is an important aspect of everyday life of a human being. Hello guys, I'm Luckshitha and my team members are Dilshad Banu and Kavitha. We all are final year undergraduate students of Male Tech Multitech Electronics and Communication Engineering. Before moving on to our presentation, I'd like to thank our mentor Dr. Prabhu sir, who guided us throughout the process. We are really delighted to present our journal, Speech Synthesizer for the Paralyzed Patient in Machine Learning. Our main objectives are to enable interaction between the paralyzed patient and their caretakers, to detect the voluntary blinks of the paralyzed patient, to navigate or select items on the screen and convert it into machine audio output, to create a less complex and affordable system. People with paralysis especially are affected with dysarthria, which is a condition where a person will have slurred or slow speech and no speech along with their no body movements. This is a result of various underlying conditions like nerve damage, spinal cord disruption due to accidents, diabetes, cerebral palsy, etc. In this case, it is mostly difficult for the caretakers and doctors to know what they are trying to say because of their unclear voice and lack of body gestures or actions. We have done a literature survey and come to a conclusion that the existing system has certain drawbacks. When more number of blinks are required for the certain command to execute, it requires more screen time and causes strain on the patient's eyes. The patient needs to learn Morse code, and also text entry rate is variable according to Morse code. Electrode placement on the scalp or around the eyes can be painful. EEG measuring devices like eye wears might cause discomfort to the patient while wearing it for a longer time. Our proposed system enables and eases communication between the paralyzed patient and their caretakers by using voluntary eye blinks. The system detects voluntary blinks of the patient and uses it as input to choose or navigate command phrases displayed on the screen. The basic requirements like food, water, washroom, and so on are displayed on the screen as command phrases and icons for the patient to choose with their voluntary eye blinks. Also, the system includes an option called Others, through which the user can access virtual keyboard if they want to convey thoughts beyond their basic necessities provided on the command phrase window. The selected commands or sentence framed on the virtual keyboard are then converted into machine audio output for reaching out to their caretakers. This is our system's block diagram. We have certain software requirements. They are operating system with Windows 10 or advanced, IDE, PyCharm or VS Code, and Jupyter notebook. We use the programming language Python 3.5. Hardware requirements are a personal computer with a processor Intel Core i3 or advanced and RAM 4 GB is required. The packages and tool requirements are Python, OpenCV, Shape Predictor, 68 coordinate, DAT file, dlib, iMutants, PyWordKit, keyboard, PyGlide, PyText 3. This is the data flow diagram for our system. After the video capture started, our system detects the phase, then the ROI is extracted, after which the eye-stated classification is done, up to which everything is done in the back-end process. Then the voluntary blink is detected for the commands displayed on the screen and it is converted into audio output. Similar process is done for the virtual keyboard as well. The live video stream of the patient eye blink is obtained with the help of webcam mounted on the system using OpenCV in machine learning using Python programming language. The frontal face of the paralyzed patient is focused over the other objects in the video frame using the DLIM. Facial landmarks are applied on the face detected using the pretrained 68 landmark predictor DAT file, which is shown here. This is the illustration of the 68 facial points, where the facial elements landmarks are marked with the number of points. The DLIB and open source image library processing while performing face detection uses the DAT file to highlight the entire face with the plots XY indicating facial points. The region of interest eyes is extracted from the face and the ROI extraction is done like the eye coordinates alone are highlighted by the plot coordinates XY from the entire face. This is the difference between the face detected image and the ROI extracted image. The eye status is tracked like it is blinked or open with the help of eye aspect ratio, which is a calculation done by the formula over here. The left eye picture is when the eye is open and the right eye picture is when the eye is blinked or closed. The bottom picture of the plot indicates the eye aspect ratio and the drop symbolizes the blink is detected. Voluntary eye blink detection is based on the duration of the blinking activity. Only the voluntary blinks will be taken into account to execute the commands. If the duration of blink is 100 and 500 milliseconds, it is considered as a natural blink. When the blink duration exceeds 800 milliseconds, it is considered as a long voluntary blink, which is shown below. We have done our system test for the face detection, and it has recorded the correct readings and wrong readings as well. The system displays the customized command phrases with icons representing the basic needs of the patient like food, water and washroom, ventilation, etc. To convey the thoughts beyond the necessities, we have the command named others, which displays the virtual keyboard with the help of it. The command selection is done with a single voluntary blink done by the user. When there is no blink detected, the command phrase is automatically changed to the following command, and same process continues until the voluntary blink is detected. Once command selection is done, the system converts the respective text command and output is read aloud. The screen time took by our system to execute different command in the command window phrase is recorded over here, and the graphical representation is given as well here. When the command other is chosen by the user, virtual keyboard will be displayed on the screen. Virtual keyboard has the alphabet, numbers, and some important character symbols, space bar, delete or backspace button, and a speak button. When the required letters are chosen to frame the sentence by blinking, the user has to select speak button on the screen, which makes the system to read aloud the sentence or word framed by them. This enables the user to convey their needs or thoughts which are not listed in the command phrase. And we can see here that hello guys is printed over the virtual keyboard. We also recorded the screen time to execute some sentence on the virtual keyboard, and we got the accuracy value as well. When the system detects no response from the caretaker towards the patient within the specified time frame, it triggers an automatic alert message. This alert message is sent through WhatsApp to the caretaker. It ensures the caretaker is promptly informed when patient requirements they require them when the emergency situation. The incorporation of automatic alert message via WhatsApp mitigates the risk of communication breakdown between the patient and the caretaker. System examined that the system proposed could perform face detection with 99% accuracy at maximum possible distance from 1.35 meter in daylight and 1.25 meter in artificial lighting during night. The system proposed also achieved detecting voluntary blinks alone from the usual blinks with 87% accuracy and varies. The screen time for the command execution into machine audio output is found to be less than 1 minute in command phrase window and vary depending upon the text entry in the virtual keyboard window. The advantages of our proposed system are it is simpler interface with easy navigation and selection of options on the window. The number of blinks and screen time required to execute each command by our system is not more than a minute. There is no additional training or Morse code learning required to operate the system. Even people who cannot read can easily understand the pictorial representation and identify the command. It is flexible and can be customized according to the person's needs. As conclusion, our system is designed in a way to help the paralyzed patient to communicate their basic necessities and thoughts with minimum voluntary blinks on screen time. Thus, the proposed system gives the patient a sense of freedom to express their needs and convey more thoughts without any word restrictions. Our system can be include certain things to improve its efficiency, like adding word predictions on the virtual keyboard, which can save even more time and patients blink to express their opinions. It can also be improved by translating the sentence form within the virtual keyboard into any communicative language with which the user prefers to communicate. It can also be improved by sending automated text and phone call alerts if caretaker is not provided within a specified time frame during an emergency situation. And that's all about our system. Thank you very much.